Welcome to this explainer. Today, we're diving straight into an invisible, literally non-stop battle that's happening inside absolutely everything around us. We're going to look closely at how heat actually transforms matter. You can think of it kind of like an energy elevator. It's this continuous, epic tug of war between kinetic energy, which just wants to tear molecules apart, and intermolecular bonds that are desperately trying to hold the whole shebang together.
To set the stage here, let's rethink a couple of things we see literally every single day. I mean, we all know that ice melts, right? But what's the actual precise thermodynamic trigger that forces that sudden structural collapse? And think about clouds. Where do they actually come from when the sky was totally clear just a few hours before? Well, whether it's the sudden condensation on a sweaty summer glass or morning dew settling on your lawn, all these macro events are dictated by one invisible, relentless law of physics.
Section 1, the golden rule of heat. Let's get right into it.
Before we can really map out how matter changes, we've got to look at the invisible force driving those changes, heat energy. Now, in thermodynamics, heat isn't just about things feeling warm. It is strictly defined as the energy transferred between materials because of a difference in temperature. Basically, it's the kinetic energy of particles in motion. When materials with different temperatures interact, you get these microscopic collisions. The faster-moving, high-energy particles literally crash into the slower ones, handing over that kinetic energy. This temperature difference is essentially the engine of our universe. It's constantly pushing energy from high-concentration areas to lower ones in this desperate quest for balance.
So it all boils down to this fundamental rule. Changes in states of matter occur because heat energy is either added or removed. That's it. That is the universal trigger. Every single phase transition, every time a solid melts or a liquid vaporizes, it's the direct result of thermal energy entering or exiting the system. It's totally binary. We're either injecting kinetic chaos into a molecular structure, or we're draining it away, which lets those molecules snap back into these highly ordered arrangements.
Section 2. Heating up, solid to gas. Let's take a ride up this elevator. The very first stop on our way up the energy elevator is melting, the transition from a solid to a liquid. In a solid state, molecules are bound really tightly together in a rigid geometric lattice. But as the material absorbs heat, that newly injected thermal energy begins to overwhelm the forces holding that lattice together. The solid physically gets warmer, which just means its internal kinetic energy is rising. Eventually, it hits this critical threshold where the bonds simply cannot contain the sheer vibrational energy of the molecules anymore. And boom, you get a massive structural breakdown, just like an ice cube turning into a puddle. If we zoom in to the microscopic level, it's actually fascinating to track how this structural collapse unfolds. Step 1. The particles gain thermal energy. They're like a sleeping crowd waking up. Step 2. This massive influx of energy makes them vibrate violently, moving with increasing random kinetic force. And finally, step 3. That kinetic energy decisively beats out the attractive forces that were keeping them locked in that rigid lattice. They break their fixed formation and just begin to freely slide past one another. The structure loses its rigidity, and the solid completely surrenders to fluidity. Moving even further up the elevator, we hit evaporation, the dramatic jump from a liquid to a gas. Think of a pot of water boiling on a hot stove. Here, the liquid is getting hit with even more intense thermal energy. While the molecules in a liquid aren't locked in a solid grid anymore, they're still tethered together by some pretty significant attractive forces. That's what gives water its cohesion and surface tension. But as we keep pumping heat into the system, those remaining bonds get stretched to their absolute breaking point. At this phase, the particle behavior becomes incredibly chaotic. The molecules are absorbing so much kinetic energy that they're vibrating at tremendous speeds and moving completely freely. Eventually, the particles near the surface of the liquid accumulate enough shear velocity to completely sever those intermolecular bonds and shatter the surface tension entirely. They literally tear themselves away from the liquid and escape right into the atmosphere as a gas. They've achieved total energetic liberation. No way they're staying put now. Now, this represents a totally crucial tipping point in thermodynamics. We've just witnessed the chaotic results of a system absorbing heat, an escalation from a rigid, quiet structure to absolute kinetic liberation, where particles go wild and completely escape their bonds. But thermodynamics is a two-way street. What happens when we throw this entire sequence into reverse? What happens when we shift away from the chaos of high kinetic energy and head back toward the impending order of low kinetic energy?
That brings us to Section 3. Cooling down, gas to solid. Time to head back down the elevator.
So the journey back down starts with condensation. This is the transition from a highly energetic gas back into a cohesive liquid. When a gas undergoes cooling, it experiences a drop in temperature, which means thermal energy is being actively extracted from the system. As the heat gets siphoned away, the gas molecules are essentially stripped of their kinetic energy. Without that high-speed momentum to keep them all apart, the attractive intermolecular forces start to take over once again, pulling those previously chaotic gas molecules back together into a dense fluid state.
What's really cool is how these micromechanics express themselves in dramatic macro events all around us. When you look up at massive cloud formations, you are literally watching water vapor systematically lose its thermal energy high up in the atmosphere. Or that moisture forming on the outside wall of a cold beverage, that is just the ambient gas in the warm air colliding with the cold glass, rapidly transferring its kinetic energy and immediately condensing into a liquid. Even the dew on leaves in the morning is a stunning visual representation of billions of gas molecules losing their kinetic battle against the cold morning air.
Continuing our descent, we finally hit the ground floor of our energy elevator. Freezing. Here the liquid state surrenders entirely to the solid state. As the liquid continues to lose heat, the temperature plummets, stripping away almost all the remaining free-flowing kinetic energy. Like putting liquid water into a freezer, it's a truly fascinating structural crystallization process. The molecules simply don't have the kinetic energy required to resist their natural chemical attractions anymore, triggering a massive system-wide structural lockdown.
Tracking this lockdown at the particle level really reveals the sheer power of those intermolecular forces. Step 1, the particles lose the vast majority of their kinetic energy. Step 2, they literally stop flowing and moving around one another. Step 3, they become completely fixed in highly organized geometric positions. Now, actually, scratch that. Unless they reach absolute zero, they never stop vibrating entirely. They still hum with baseline atomic energy. But their macroscopic movement? That's over. The chaotic fluid has been pulled into a perfect, unyielding crystalline lattice.
Section 4. Why state changes matter. Let's bring it all together.
Let's bring it back to our core principle for a second. Changes in states of matter occur because heat energy is either added or removed. This isn't just some boring textbook definition. It is the grand unifying theory of the physical environments we navigate every single day. Understanding and manipulating this transfer of heat, riding the energy elevator up and down by controlling kinetic energy and intermolecular forces, it's the foundational basis for everything. From the global weather patterns shaping our climates, all the way to the advanced thermodynamics powering our civilization's internal combustion engines.
So here's a thought to leave you with. Next time you step outside and brush past the morning dew, or stand in the kitchen watching a pot of water begin to roil and boil, ask yourself, are those microscopic particles gaining kinetic energy, or are they losing it? Because once you start looking at these everyday moments as an invisible, relentless war between thermal energy and atomic bonds, while the physical world around you becomes a truly fascinating place.